Welcome to IDSKT. Let's explore an important topic shaping the future of defense and global security. I'm the founder and director of International Defense Security and Technology, a California-based nonprofit think tank dedicated to research and analysis on global defense, security, and emerging technologies. I also serve as CEO of Interplanix LLC, a New Mexico-based company advancing satellite risk analysis, orbital debris forecasting, and space security frameworks to ensure mission assurance and resilience. Previously, I served in leadership roles at India's Defense Research and Development Organization, DRDO. Most recently as Director of the Systems Analysis, Modeling, Safety, and Quality Cluster at DRDO Headquarters, New Delhi. This channel brings you deep insights into the global security ecosystem, from geopolitics and emerging military technologies to cyber, space, and system-level analysis of tech trends and their interrelationships. Subscribe and join us as we decode the forces shaping the future of global defense and human security.
Today we are diving into a revolutionary leap in vibration sensing, one that's redefining precision measurement across defense, medicine, and quantum computing. It's called the Quantum Photonic Vibrometer, or QPV. This isn't just a next general upgrade, it's an entirely new way of sensing, built on quantum light and entangled photons. If that sounds like science fiction, you're not alone. But it's here, and it's real. For decades, we relied on mechanical sensors and accelerometers to measure vibrations. Then laser Doppler vibrometers came along, using interferometry to boost accuracy without physical contact. That changed everything. But even laser systems have limits, especially when it comes to detecting the tiniest motions or operating in challenging environments. That's where quantum photonics steps in. The Quantum Photonic Vibrometer uses squeezed light with quantum noise reduced in specific ways to measure vibration at nanometer or even picometer scales. It splits a beam of quantum light into two paths. One reflects off a vibrating surface. The other acts as a reference. When the beams recombine, they reveal phase shifts that tell us exactly how the object moved, even if it moved only a billionth of a meter. And here's the kicker. These systems can suppress noise like no classical device can. Using entangled photons and advanced quantum algorithms, QPVs filter out environmental interference, laser instability, and even thermal noise. That means sharper readings in noisier, messier real-world conditions. This has huge implications. In aerospace and defense, QPVs can monitor the structural health of aircraft and satellites with extreme sensitivity. They can detect micro-vibrations caused by material fatigue or turbulence, vibrations that traditional sensors might miss. In stealth operations, they can even pick up on faint motion patterns from hidden vehicles or objects. In the industrial world, these vibrometers can monitor bridges, dams, or turbines in real time without touching them. That allows early fault detection, preventing disasters before they happen. And in medicine, imagine detecting the subtle tremors of Parkinson's disease, or even monitoring a patient's heartbeat through a sensor that doesn't require any contact. That's the promise of QPV. But perhaps the most exciting part is what comes next. New systems can even detect vibrations without line of sight. Using scattered light and quantum-enhanced signal processing, QPVs can reconstruct motion from surfaces hidden behind walls or underground. This opens doors for underground mapping, buried object detection, or surveillance in environments where traditional optics fail. Quantum Computing Inc., or QCI, has already launched a commercial QPV that uses single photon detectors and something called quantum parametric mode sorting to isolate vibration signals buried in background noise. This lets it operate in dim, cluttered, or acoustically chaotic environments and still pull out usable data. From material recognition in manufacturing to tracking vibrations in dense forests or under oceans, QPVs are being explored for everything from safe mine detection to next general voice detection. That's right, by picking up tiny vibration patterns on surfaces like glass or walls, these sensors could reconstruct speech, even in noisy environments. Of course, challenges remain. These are quantum systems, after all. They depend on delicate components like nonlinear crystals and single photon detectors that need careful calibration and stable environments. And the costs are still high. But that's changing fast. Efforts are already underway to shrink everything down into system-on-chip designs. That means compact, affordable QPVs that could one day fit into smartphones, wearable medical devices, or next general robotics platforms. The takeaway is this: quantum photonic vibrometers are not just a scientific curiosity. They're real tools with real impact, and they're on the edge of transforming how we sense, secure, and understand our world. Whether it's for defense, diagnostics, or deep space exploration, this is a technology to watch.